Okay, so this was the problem that took all period, and we still didn't finish it, right?
Good times.
Good times. All right, so get your notes out if you're so inclined. Let's have a look at this. Quiet, please. Let's get going. We got to get through this. So we're trying to find. Remember, we're trying to find. Did I like leave the first page? Oh, I did. I'm way up there. Okay, so this was. Boy, lots of stuff there, isn't it? So this is the problem that we were trying to solve. We're trying to find the points of inflection and relative extrema for this trig function on this interval, right? And we did a lot of stuff, right? We found, let's just kind of rehearse or review what we did on Friday, and then we'll pick it up from there. So first of all, we looked for the first derivative critical numbers by differentiating and setting determining where the first derivative was undefined and where it was equal to 0. When we differentiated, remember the first thing we did was we rewrote this complicated looking trig function involving secants and tangents. We wanted to rewrite that in terms of sines and cosines. And we got this fraction, right? So that's very useful to us because then we know that the zeros of the denominator are the places where the function is undefined, and we found those, right? Cosine of x minus pi halves is equal to 0 when x minus pi halves equals, what did we decide it was? It was pi, 2 pi, 3 pi, right? So theta equaled, I think it was the odd multiples of pi halves, right? Mm-hmm. So we did, I don't know if I still have that stuff up here or not. But we, right here, I guess, isn't it? No?
Yeah, equal.
That should say cosine.
You don't know the page of it. Next page, maybe?
Oh, 0, yeah, undefined, yeah, you're right. So it would be maybe, I mean, this thing got there was so much to do.
How many pages long is this?
It was many. It was many pages.
Did you record it?
Oh, there it was, right there it was.
Are you recording?
No, I did record it, and I am recording this.
Okay.
Okay, and it's already up online. So here's the page where we found the zeros of the denominator, right? We just called this whole thing theta, right? And the cosine of theta equals 0 when theta is any odd multiple of pi halves, right?
Yeah.
And so we found what all those were, but then we determined there was probably an easier way to do this, which was like that, right? Cosine of theta equals 0 when theta equals, this is our best way to do it, is to say just generically an odd multiple of pi. This looks complicated, but we recognize 2n minus 1. If n is an integer, then 2n minus 1 is just 1 less than an even integer, right? Which makes it an odd integer. Agreed? You double an integer, it becomes even, subtract 1, it becomes odd. So 2n minus 1 times pi over 2, and then we figured out which values of n were going to give us results for x that were inside our domain, right? Theta is really x minus pi halves, and so we just did the algebra. We distributed the pi halves, we solved for x, and we got the answers. X equals n pi. Yep. Right? When all the dust settled, when we solved for this expression right here, we got the answer x equals n pi, which is convenient. Any integer multiple of pi. And on our interval, right, that's just going to be pi, 2 pi, and 3 pi. So those were the places. Those were the places where I got to go back and find. This is right there. Those were the places where we had vertical asymptotes, right?
Yep.
Okay. Did a very similar thing for the top of the fraction. I think that was this first one right there, right? For the top of the fraction, we know that the derivative equals 0 when the top of the fraction is 0, and the sine of x minus pi over 2 equals 0 when the argument, theta, x minus pi over 2 equals any multiple of pi, right? On the unit circle, where is sine, which is the vertical component, equal to 0? Well, there and there, right? So it's any integer multiple of pi, right? So if we solve this for x, if we add pi over 2 to both sides, we just get x equals n pi plus pi halves. And then we just pick the values of n that gave us critical numbers inside our interval, right? Between 0 and 4 pi, that worked for n equals -1, we got pi halves. For n equals 1, we got 3 halves pi. For n equals 2, we got 5 halves pi. And for n equals 3, we got 7 halves pi. Got how to count. Okay, make sense? And so this is where we ended up then. I think that is, oh no, we did take the second derivative. Okay, or we were in the process of doing that.
Yeah, we're on the second derivative.
Okay. So this is where we left off. Right? Okay. That's a lot, but now we're gonna look for our, we're gonna take the second derivative. So we were in the process of doing that, and it's kind of not a very fun thing to do because we've got to use the product rule, right? And so we had the first times the derivative of the second plus the second times the derivative of the first, right? And so we did some stuff then. We said, okay, this is where we were kind of leaving off. We could simplify both sides. Secant of hand times secant squared of hand is secant cubed of hand. Secant or tangent times tangent would give us a tangent squared. And then we have another secant there, another factor of secant. And so we ended up there. And then we factored out a secant. We had a common factor. We factored out a secant hand, right? And that's where we left off. So that's our second derivative. I can never remember. I don't think this is one. I don't think it is. We were just exploring that, but I never remember, but I always just figure it out for myself rather than waste those brain cells remembering something. So here's how you can very quickly relate secant squared and tangent squared using the Pythagorean trig identity. All you do is you just start with the regular Pythagorean, I think we've done this before, the regular Pythagorean identity, sine squared theta plus cosine squared theta equals 1. And then if I want to get secants and tangents, what would I divide both sides by? Cosine squared, right? Does that make sense? So we'll divide both sides through by cosine squared theta, which gives us, on this side, I get sine squared over cosine squared, which is tangent squared, right? Plus 1 equals secant squared. Right? And so what do we probably want to do here? Well, we probably want to trade this. We can't, unfortunately, secant squared plus tangent squared. And I kind of thought it was going to be this way. It isn't a trig identity. It'd be nice if that was things. It'd be nice if that was just like 1 or something. That'd make things much easier, but it's not. Secant squared and tangent squared are on opposite sides of the equation, and so I'd have to subtract 1 to get it to the other side. Does that make sense? Yeah. So the best we can do, though, is we could make a trade of tangent squareds for secant squareds, or vice versa. Well, what would we rather end up with here? Secant squareds, wouldn't we?
Yep.
Right?
Why?
Because we've got a secant out there also.
Yes.
Right? Does that make sense?
Yes.
Okay? And I guess we really could do it either way, but let's trade this tangent squared then for a secant squared minus 1.
Yep.
Does that make sense? Okay, so then we end up with, if we do that, we end up with secant of hand times, and did we, oh, never mind, we're good. Secant squared hand plus the quantity secant squared minus 1. we could combine like terms here though, right? Agreed? Okay, and so we end up getting secant of x minus pi halves times 2 secant squared minus 1. Now that looks, I know that looks terrible. But what are we trying to do with this anyway? You know, really all we're trying to do is just find a, yeah, we want to be able to write this in a way so that we could maybe use the second derivative test, although we don't really need to. But we need to be able to set it equal to 0, or find out where it's undefined or equal to 0, right? And we're going to be able to do that because we could, this is already factored, right? Does that make sense? It's going to be undefined. What's on the bottom of the secant function? Cosine, right? And so this thing is going to be undefined. We don't even really have to do this work because can't we already see that it's going to be undefined in the very same places where this was undefined? Would you agree?
Yes.
Okay, so we already know that there are going to be no critical numbers where the function is undefined, and so we don't even have to bother looking for the places where the second derivative is undefined because they're going to be the same answers we got for the function. Does everybody get, that's really important. Does everybody get that? Why waste your time?
Does the plus one make any difference? I don't remember from the other equation if the plus one would make a difference.
The plus, which plus one?
On our actual equation, we have a 1 in there, but I don't think it's gonna make a difference. Or minus 1, yeah.
Go forward.
On the second derivative at the end.
Oh, at the end of it?
Yeah, I don't
Oh,
think
no,
that would
no,
make
no.
a difference though.
Okay,
Yeah.
right, so okay, that's an excellent question. So if we go back to the second derivative,
Like I know it won't make a difference on the formula, but I was thinking about maybe the values of theta.
there it is. Okay, excellent question. Excellent question. So if we rewrote this in terms of sines and cosines and everything, we're going to do a lot more of this in the future. We'll get a lot more practice. But a function is undefined wherever individual parts of the function are undefined, right? In other words, the function, a way that mathematicians would say that is functions inherit the discontinuities of their factors and terms, right? Any kind of internal discontinuity, the function is going to get. We're looking for red flags. Whenever we're looking for places where functions are undefined, we're looking for red flags. Where are they going to happen? In the bottom of fractions, right? Well, the only fractions that show up here are the secants. Secant is 1 over cosine, right? So I could go through the process of rewriting these as 1 over cosine, but I'm just going to save myself the trouble of doing that because we already know that we had that problem with the original function and we already took care of it. We did all the work. We found out that when the bottom of the fraction was cosine, the places where that caused problems was at pi, 2 pi, and 3 pi, and we have vertical asymptotes there, right? So all we have to do then is just find out where the second derivative is equal to 0, right? But this is already factored. So when we set the second derivative equal to 0, we know where those are going to happen. It's going to happen where either secant equals 0, right? So there's, by applying the 0 product property, where this factor equals 0 or where that factor equals 0. So where does secant of x minus pi halves equal 0? Or where does 2 secant squared x minus pi halves minus 1 equals 0, right? And we'll just solve that.
I thought you said we don't have to do that because we know cosine is in.
Okay, but that's where it's undefined, not equal to 0, right?
Okay.
Right? Make sense? Okay.
Does or mean both?
I should say and, not or.
Does that mean both?
Yeah, or means, or is the wrong word. I should say and. The solutions are going to be, I always write or up there. Actually, no, it is or. Because it can't be one and the other at the same time.
Yeah.
Right. Does that make sense?
You don't do.
But you have to take
You
both.
can pick.
You have to find both.
Yeah.
Yeah, you have to find all the critical numbers. Critical numbers occur here or there, but we need to know what all of them are so we can test them, right? Okay, so this is, let's look at these. I know seems like a lot of stuff, and this is a long problem. But, it's, at some point, you're all gonna have to do problems like this. It is, admittedly, it's a long problem. Okay. Yeah.
Questions on the test like this.
No, I wouldn't put one this long.
Okay.
Oh,
They don't take us.
Yeah, just do one problem.
right now, it's 3.5 hours.
But I tell you what I will do, there's gonna come a point, and I don't know when this will be, but there's gonna be a point in the class where I am gonna maybe do a different kind of test for you guys, where you're gonna have to do, like, write out, not on the computer. I wanna see your work on
I like that, man.
doing a problem like that, you know.
I like it.
Okay, do not, listen, don't get sidetracked, you can't do that. If you do, I'm just telling you, the way your brain works, if you allow yourself to think about other less important things right now, you're gonna get sidetracked, and it's gonna interrupt your train of thought, and it's not gonna work for you. So where does this happen? Well, let's rewrite this as 1 over cosine, right? So, okay, and I don't even really have to go any further, do I? Does that ever equal 0?
No.
It doesn't. And in fact, if we were to look at the graph of a secant function, do you remember from last year what the graph of a secant function looks like?
Yes.
That's the one, it's kind of the weird looking
Yeah.
one that does, secant would be 1 over cosine, so it'd be like,
It's like,
yeah, it'd be like this.
Yeah.
Right?
how did that go?
Right? Does that make sense?
Yeah.
Does that function ever pass through, it has no zeros, right?
Yeah.
So we would expect that, yeah, this could never happen. So there are no critical numbers where secant of hand equals 0. Yes, ma'am. Oh, maybe it was our original equation. But we never, I don't think, Clancy, we ever actually looked for zeros. We could have.
Yeah,
We said it, we're we just said we're cosigning.
Right. Okay,
Really?
hey, girls, put that away. What about this other one, though? So now we've got this other, I think it's right there. Yeah, this guy, we gotta look for this one, right? So the last one we gotta check for. So there were no critical numbers here, right? How about this?
Do you think it?
Okay, so where would this equal 0? Well, if we're gonna solve this trig equation, the first thing we're gonna do is we're gonna solve for secant, right?
Yeah.
So what are the steps in order to get the secant by itself? And be very careful with this. Okay, we're gonna add 1. Then we're going, Jolie, what's next?
You're gonna move the 2 over.
How do I do that?
You're gonna have to do the split up.
No, I'm just isolating the secant. I add 1, then what do I do?
Divide by 2.
Divide by 2, okay, good. Okay, then what's the last step? Last step. Grant, what's the last step? Okay,
Do you square root it?
pay attention. Yeah, we square root it. Good. Because remember, secant squared really just means the quantity secant squared, right?
Yes.
Okay. So we'd end up
Can
with,
we do that out on the board?
yep, you bet.
Okay.
Right?
Yeah, and then we find where it equals. Oh.
Okay, so now I've got a square root.
Yeah.
Right.
Oh, okay. I gotta have.
So I get secant of x minus pi halves equals plus or minus the square root of
Square root 2 over 2.
square root 2 over 2.
So, but don't you have to do something?
And now you find theta where it equals square root of 2, and then you plus.
Right.
I don't understand why is it not. Why is it square root 2 over 2 instead of 1/4?
Because I'm square rooting.
Not square root.
right? So it's 1 over the square root of 2, which is just square root of 2 over 2, right?
Oh, could you
Okay.
write it?
However, think about this now. Secant is the reciprocal of cosine, right? So this looks like you're going to get some places, doesn't it? But if we write this as 1 over
Square root of 2.
cosine of hand equals
Oh.
plus or minus square root of 2 over 2, I've really got to flip both sides, don't I?
So it's
And
just
so look what I get. Yeah, I get cosine of hand is equal to plus or minus 2 over the square root of 2, which is the square root of 2. Right? The reciprocal of this is just 2 divided by the square root of 2, which is the square root of 2, right? Okay, does cosine ever equal a value greater than or less than, greater than 1 or less than negative 1?
No.
No. So are there any critical numbers here?
No.
No, there aren't. Right?
So, could you have known that?
After all that work.
Oh, you don't.
Could we, and the answer is no, we couldn't have known that. We couldn't have known that.
That is so annoying.
So what do we do with the answer?
So our answer is,
0.
no, our answer is if we go back here, so we need to know what is the sign of our second derivative, and it's never gonna change.
Positive.
So I gotta find that sheet. Man, I have so many sheets open. Here it is. Okay,
So there are no extremas? Or
so between, right, so right here, so we end up with,
Wait, the cosine is, why is it no cosine?
what?
Sorry.
Are you gonna ask them?
right, so on our, let me go to our table. So on our table, we didn't get any places where the second derivative changed concavities, right? Okay, so let's make this row. So then all we've got to do here is we just have to know by using the second derivative. I mean, we don't even really have to do this because we know, everybody pay attention to this, please. So we know that there's no place where the second derivative can change concavities. And the question just asked for inflection points, right?
Yeah.
So let me ask you this real quick. Could the second derivative be positive there and negative there?
No.
It could. Okay, because remember, this
Yeah,
is
because the person.
because the vertical asymptote splits that universe into separate parts, right, that are completely independent, right?
Yeah.
Okay, well, all you have to do,
Plug it back in.
now just hang on. We don't have to. It's not asked on the problem. The problem wants to know where there are points of inflection, where there are places where the second derivative, if there are values in the domain, where the second derivative changes sign. And there aren't any, right? Because these places right here are not in the domain, right? That means that for every value of x greater than 0 and less than pi, the sign of the second derivative has to be the same. It can't change because there were no inflection points. It might be. I don't know. I just threw that in there randomly. It might be minus positive. If the question, and I'm just gonna kind of save you some work here. If you saw this on a test, you wouldn't have to go any further because you already know there are no inflection points. Now, if the question asked, where is it concave up and where is it concave down, then you'd have to find out. Then we'd have to check the sign of the second derivative inside this interval, right? But it doesn't ask that. All it wants to know is, are there places on the function where it swings from concave up to concave down? And no. In this universe, it's always either concave up or concave down. In this universe right here, it's always consistent, right? See what I'm saying?
Is it like a straight line or is it like a mountain?
It's gonna be neither because it's a vertical asymptote. See what I'm saying?
So is it like the secant, the things you were showing us before, is it like that?
Yeah, we're gonna have asymptotes there, right? These are vertical asymptotes, exactly. Okay, so the only thing we have left to do, and this is another thing, that it's important to be able to relate here. we have to find whether our first derivative critical numbers are relative extrema or not, because we never did that, right?
Right.
So what are our options? Our options are, we can either use the first derivative test, right? Remember what the first derivative test is. We have to pick test points surrounding each first derivative critical number and check the signs to see if it goes from increasing to decreasing or vice versa, right? Or we can use the second derivative test. It's been a while, but you remember what the second derivative test is. That's the one that says if we know that we have a zero first derivative with a positive concavity, right? With a bowl up concavity, then doesn't that necessarily mean a minimum?
Yeah.
See what I'm saying? So you have to decide now, what's harder to do? To me, it would be easier to just evaluate the second, as ugly as it is, just evaluate the second derivative at pi halves and see what the sign is, right? And so you're actually going to find out what the concavities are anyway, even though you didn't need to, right? We just want to know what is this sign here. So we'll go back to the second derivative.
Wait, are we gonna do it?
Yep, we're going to do it.
Well, I thought we didn't need to.
Well, we don't need to, but we can, right?
But we
Well, no, I mean, you have to do one or the other, right? You have to either use the second derivative test or the first
Wait,
derivative
what are we
test.
trying to find out how big?
You're trying to find, we're testing the first derivative critical numbers to see if they're extrema. So we're gonna use the second derivative test, being as we already went through all the work of finding this thing.
Yeah.
Right.
How are we gonna know if they're extremists if we have vertical?
Let's take a
Are we
look.
gonna have to plug in different points away from
No, because, see, this is why it's better to work further down the table. Because all we have to do is evaluate 1 point instead of 2. We can just evaluate this function at pi halves and see what we get. So let's figure this out. At pi halves, if I plug in pi halves, I get secant of pi halves minus pi halves. Secant of 0. What's the secant of 0?
0.
Well, it's 1 over the cosine of 0. And what's the cosine of 0?
1.
1, right? So I'm going to get back 1 times 2 times 1 minus 1. So it's going to be positive, isn't it? Right? Do you agree?
Yes.
If I plug in pi halves, I get 1 times something positive, times 1. So we were right, that is positive. So what does that tell us then? The second derivative says if it's concave up and it's a horizontal tangent, I know that this definitely is a minimum. Remember, the positive second derivative means a happy function, right? Okay. What about at 3/2 pi? Well, the secant of, let's go through that one. The secant of 3/2 pi minus pi halves. That's the secant of pi, which is -1, right? Because it's the reciprocal of cosine of pi. Cosine of pi is -1, right? And over here I'm going to get, secant squared is going to make that positive. So I'm going to get negative times positive is negative. And so this is definitely a maximum, right? Because the second derivative test tells us that we have coupled a horizontal tangent with downward concavity, right?
Yes.
What about up here? 5/2 pi. What do you think is going to happen? 5/2 pi, we're going to get the secant of 2 pi, which is the same as the secant of 0, right? So that's going to be 1. Over here, no matter what, we're going to get back positive, right? So we get positive. And then finally, at 7/2 pi, we're going to get 3 pi, right? 7/2 pi minus pi halves is 6/2 pi, 3 pi. Same as pi on the unit circle, so that's going to be just like this column, right?
Most of the time, isn't it every other?
Yeah, it's a lot of times you'll see this kind of symmetry, yeah. Not always, but. So that's it. So that's everything we need to know about the function. There are no points of inflection, but we have minima and maxima at these values of x that we could put into our function and find the values of y if we wanted to, right?
This is number 10.
Yeah. Was that on the actual assignment?
Yeah.
Not that exact.
No, it wasn't.
No, not
No, it
that
wasn't.
exact.
I picked a hard one.
A hard one.
This was, I picked this one. This was harder than, yours is easier than this.
Oh, okay, I think so.
It's not too.
No, I would
I
pick.
picked a harder one of them.
Yep.
So the relative extrema is just.
Right? Okay, 4 minutes. Okay, I'll take a roll.